In one of my earlier videos, I talked about how many batteries you need for a 3000-watt inverter, and I strongly recommended using a 48-volt battery system. But what if you already own a 12-volt 3000-watt inverter? That's actually a very common situation, and a lot of people have been asking, how many 12-volt batteries do I really need to run it properly? The short answer is simple. If you're using lithium batteries, you'll usually need 3. If you're using lead-acid batteries, you may need around 13. That's a huge difference, and in this video, I'll show you exactly why. We'll go step by step, starting with inverter efficiency, then battery calculations, and finally, how to figure out the correct wire and fuse sizes. Let's start with the inverter itself. A 3000-watt inverter can deliver up to 3000 watts of usable alternating current power to your appliances. But there's something many people forget. Inverters are not 100% efficient. Some energy is always lost during the conversion from battery power into household power. Most good inverters are around 90% efficient. That means the battery actually has to provide more power than the inverter delivers. To calculate that, we divide the output power by the inverter efficiency. 3000 watts divided by 0.9 equals 3,333 watts. So, even though your inverter says 3000 watts, your battery bank must supply about 3,333 watts. That extra power turns into heat and conversion loss inside the inverter. And this is exactly why battery sizing matters so much. Now let's look at lithium batteries first, since they're usually the better option for modern off-grid systems. A common lithium battery is a 12-volt 100 amp-hour battery. Most of these have a built-in battery management system, also called a battery management system, that limits how much current the battery can safely provide. In many cases, that limit is 100 amps. To find out how much power one battery can deliver, we multiply battery voltage by current. 12.8 volt multiplied by 100 amps equals 1,280 watts. So one battery can only provide 1,280 watts. But remember, our inverter needs 3,333 watts. Clearly, one battery is not enough. So now we divide the required power by the power from one battery. 3,333 divided by 1,280 equals about 2.6. And since you can't use part of a battery, you round up. That means you need 3 12-volt 100 amp-hour lithium batteries connected in parallel. That gives your inverter enough current to run safely without pushing each battery too hard. But what if you're using larger lithium batteries, like a 12-volt 200 amp-hour model? That can reduce the number of batteries you need. We'll calculate that next. Now let's see what happens if you use a larger lithium battery. For example, a 12-volt 200 amp-hour lithium battery with a 200 amp battery management system. These larger batteries can deliver much more current, which means fewer batteries may be needed. Let's calculate the maximum power from one battery. 12.8 volt multiplied by 200 amps equals 2,560 watts. Now divide the inverter's required power by that number. 3,333 watts divided by 2,560 watts equals about 1.3. So in this case, you would need 2 batteries connected in parallel. That's one big advantage of higher capacity lithium batteries. You can reduce the number of battery connections and keep the system simpler. But now we need to talk about something just as important: the wiring. Here's the diagram we'll use for this setup. It may look a bit overwhelming at first, but stay with me. I'll explain everything one step at a time. A 3,000-watt inverter running on a 12-volt battery system pulls a lot of current. To calculate that current, we divide power by battery voltage. 3,333 watts divided by 12.8 volt gives us about 260 amps. That means your battery bank could be delivering around 260 amps when the inverter is fully loaded. That's a lot of current. and high current means thick cables are absolutely necessary. But before choosing wire size, we need to add a safety margin. A good rule is to add 25%. So, we multiply 260 amps by 1.25. That gives us 325 amps. So your cables and your main fuse should be able to safely handle at least 325 amps. At first, you might think one large cable would be easiest. But once cable sizes get very large, they become stiff, expensive, and difficult to work with. That's why many people split the current across two cables instead. To do that, divide 325 amps by 2. That gives about 163 amps per cable. That makes cable selection much easier. Instead of one massive cable, you can use two properly sized cables in parallel. This is often easier to install and gives you more flexibility. Now let's talk about the fuses. Since we are splitting the current across two separate cables, each cable should be protected with its own fuse. That is the safer and more accurate way to do it. Each cable is carrying about 163 amps, so the fuse on each cable should be rated just above that, while still protecting the wire. A 200 amp fuse on each cable is a good choice. That way, if one cable ever develops a fault, its fuse can disconnect it before the wire overheats. This gives you better protection than using one large fuse for both cables together. Never skip this step. Proper fuse protection is one of the most important parts of building a safe battery system. Next, we need to look at how the batteries connect to each other, and why using bus bars can make your setup much cleaner and safer. When connecting multiple batteries in parallel, many people connect battery to battery directly. That can work, but it can also create problems. Too many cable lugs stacked on one battery terminal can make the connection unsafe. A cleaner and safer method is to use bus bars. With bus bars, each battery connects to a central positive and negative connection point. This keeps the wiring organized and helps balance the current more evenly between batteries. It also means each battery cable only needs to carry the current from that one battery, not the total system current. For example, if each lithium battery can supply 100 amps, that is the maximum current each battery cable needs to handle. Again, we add a 25% safety margin. 100 amps multiplied by 1.25 equals 125 amps. So each battery cable should safely support at least 125 amps. It's also a smart idea to place a fuse on each individual battery. Here's why. If one battery develops a short circuit, the other batteries could dump their energy into that faulty battery. That can damage equipment and create a serious safety risk. Individual battery fuses help prevent that. And remember, even though lithium batteries have a built-in battery management system, that system is not a replacement for a real fuse. The battery management system protects the battery during normal operation. A fuse protects the wiring during a fault. You need both. Now, let's talk about lead-acid batteries. This is where things change a lot. Lead-acid batteries can technically deliver high current, but doing that regularly shortens their life. A good rule is to keep them around a 0.2 C discharge rate. That means a 100 amp-hour lead-acid battery should ideally only deliver about 20 amps, but your 3000-watt inverter at 12 volt may need around 250 amps. So, how much lead-acid battery capacity would you need? To calculate that, divide the required current by 0.2. 250 amps divided by 0.2 equals 1,250 amp-hours. That means you would need around 13 12-volt 100 amp-hour lead-acid batteries connected in parallel. That's a lot of batteries, a lot of space, a lot of weight, and often more expensive in the long run. That's why lithium usually makes much more sense, even if the upfront cost is higher. Before we wrap up, I want to mention one more thing. Just because you can run a 3000-watt inverter on 12 volt does not always mean you should. At 12 volt, the current is extremely high. That means thicker wires, larger fuses, and more stress on every connection. If you're building a new system, moving to 24-volt or even 48-volt can make everything easier. Lower current, smaller cables, less voltage drop, and usually a more efficient setup overall. But if you already own a 12-volt inverter, now you know exactly how to size your batteries and build the system safely. I hope this helped make things clearer. And now I'd love to hear from you. Are you running a 12-volt system, or are you thinking about moving to 24 or 48-volt? Let me know your setup in the comments. If you found this helpful, don't forget to like the video and subscribe to Battery Hacker for more simple battery and solar guides. Thanks for watching, and I'll see you in the next one.